All right. So. Bleep-a-deep-a-dee. One of the major applications, one of the major kind of like developments developments for calculus, or like the cause for the development of calculus, is the desire to find the slope of other functions than just plain old lines. Okay? So like the slope of a line, that is the rate of change of a line, we can find that very easily, right? We know how to do that. You take 2 points on the line, use the slope formula, you get the slope of the line. You count rise over run, whatever kind of thing. Okay? What is special about the slope of a, well, let's say here. Does the slope of a line change? Let me ask it that way. Oh, sorry. If I give you a line, will its slope be different at different places on the line?
Oh, a line.
No. Okay. Slope of a line does not change when you're given a line. The slope doesn't change. Okay. So it's very easy to calculate the slope there. But then consider a function more like this. Okay. What can we say about the slope of this function? Or any ideas about maybe things you can think, or things you might think might be true? What's that? Okay. So the curve looks exponential. True. Maybe we can also further say it's an example of exponential growth, right? So it's growing, it's increasing, okay? But think again in terms of the slope, or that rate of change of this thing. Okay, so the slope is increasing. True, that's a true statement, okay? So also, what sign might this slope be? Positive. Why do you say positive? Because, our function's increasing here, so we'd expect to have positive slopes. Because doesn't a line, when it's increasing, its slope is positive, and a line, when its slope is, when the line is decreasing, its slope is negative, right? Okay, stuff like that. And so here we see this function is everywhere increasing, and so maybe the slope is everywhere positive. Do we expect the slope on this curve to be the same everywhere? No. Okay, and why maybe do you think that might be? What's being indicated here? How's that being indicated in this graph? That maybe not the same everywhere. What's that? Okay, exponential. Any other ideas? Yeah.
It's a curve.
It's a curve, right, as opposed to a straight line. Exactly right. Okay. So yes.
Wait, is the secant line? Is that the line that only touches it once?
Two times. So we're going to get to that in just a second here. So so you guys, you already can see, right, this is what mathematicians do, right? They kind of run across stuff like this, and well, we feel like we should be able to say that this line, this function here is increasing, and so maybe we can say that its slope is positive, right? And some other things too, right? But of course, you want to try and be more formal with it. And so we take these big ideas and we try to then boil them down into a formal kind of definition. How can we actually find the slope of a function? Especially considering that the slope of a function is this kind of function here is changing depending on where we are. So in actuality, we need to really be able to find the slope at a single point. Because at any given point here on this curve, it looks like the slope might be different. Slightly different in some cases, or more different in other cases, right? But how do you find the slope at a single point, right? How do you find the slope at a single point? Well, you start by finding the slope at 2 points, which is the idea of a secant line. Now, the word secant, right, that comes from stuff we learned about in trigonometry, but also in geometry, okay? Back in your circles unit in geometry, where you had a line intersecting your circle at 2 points, that's a secant line. What do you call a line that intersects your circle at 1 point? Tangent, right? Okay, and so our goal is to use a secant line intersecting at 2 points, and then somehow to manipulate it to get down to just a single point, so we have then a tangent line. Okay, that's what we're going to do here. That's kind of like the trick for how mathematicians were able to take a seemingly impossible thing, coming up with a slope using just a single point, from a possible thing using a slope between 2 points. So, to this picture right here, right, you'll see we already have 1 point designated here. I'm going to designate the coordinates for this other point too. Again, we're trying to be very generic here. You'll notice we're just using a number, C, and then f of c, right? Very generic here because we don't want to have to be hampered down by very specific caveats or whatever kind of thing, or numbers. Okay? I'm not going to call this next point, though. I'm not going to use D or anything like that here. We're going to define this x coordinate right here in a bit of a different way. We're going to go out a distance, and I'm just going to pick some unknown distance h there. So if this x-coordinate is c, we go out a distance of h from it to get to this point. How can we express this x-coordinate? C plus h. Exactly right. And if that's c plus h, and we go up to this point and then over, what's this y-coordinate? What can we express this y-coordinate as? F of c plus h, right? Again, this c plus h is the x-coordinate, which gets us to this point on our function. This is f right here. And so then the y-coordinate here would be f of c plus h. So again, we are building towards finding the slope at a single point, finding the slope of the tangent line. We're building towards that by starting with the secant slope, because we know how to find the slope between 2 points, right? So this point's coordinates is c comma f of c, and this point's coordinates right here are c plus h, comma f of c plus h. Okay? So, what is the slope of the secant line between these 2 points? Well, it'll be m equals y2 minus y1 over x2 minus x1. Okay. What is our second y-coordinate here? F of c plus h. F of c plus h there. What's our first y-coordinate? F of c, the other y-coordinate there. So minus f of c. All over. Okay, what's our second x-coordinate there? C plus h minus, and what's our first x-coordinate? C. So there's our slope formula. Very generic. Okay, lots of variables going on there, but just very generic secant formula for any kind of curve. Okay, secant slope formula for any kind of curve. Is that the best we can do with this slope formula, though? Is there anything else we can do with that?
Take out the c of the line.
The c's will cancel in the denominator, right? We have a positive c and minus c, so they'll cancel. And so we're left with f of c plus h minus f of c all over h, okay? And we had a name for this in the past. What do we call this thing? The difference quotient. We'll get to the derivative in a second. This is just without the limit, it's just the difference quotient. Okay, so right now this is just the difference quotient because there's a difference and a quotient. Difference quotient. Okay. So now we have this generic formula for the secant slope, that is the slope between 2 points on a curve. How are we going to take this? And get it to yield a slope at a single point, a tangent slope? Well, let's go down here, right? So what if we wanted to find the slope of a line at a single point instead of 2, right? So let's say in this specific case on our curve here, we want to find the slope at this single point right there. Okay. If we were to eyeball this, we could kind of like draw a tangent slope. It would look something like this. Okay. Something like that. That's what our tangent line would look like. Okay. And you could maybe like eyeball what the slope there is going to be. I mean, we could at least say, what's the sign of that tangent slope going to be? It's going to be negative, right? Okay. Which, by the way, the function, what's the function doing in this interval right here? What behavior do we see? It's decreasing, and the slope there is negative, right? The slope of the tangent line is negative. Okay. Maybe there's a relationship there. So great, we can kind of eyeball it. We can see it's going to be negative, but what is the exact value, right? We want to find the slope at that single point right there. What is that value? Well, what can we do? Well, with what we know so far, we can say, all right, let's pick like this point, for example, okay, here, and we can find the slope between these 2 points. Okay, so we can find that secant slope, right? And that's exactly what this calculation is right here, right? You can see f of 1, that's our y2, and then our x2 right there, and then there's our x1 and y1 right there. So we're just going to evaluate this. So f of 1, well, according to this graph here, what is f of 1? 2. Okay, minus, what's f of negative 1? 2 again, over, and then 1 minus negative 1 is the same thing as 1 plus positive 1, so it's going to be over 2. So 2 minus 2 is divided by 2, 0 again. And so our slope is 0. Okay, our secant slope is 0. Well, 0 is close to being negative, right? Again, we can see here that the slope of this single point, if we eyeball it, it looks like it's going to be negative. 0 is pretty close to a negative number, right? But how can we get a better approximation here? How can we get a better kind of estimate of what that tangent slope is going to be? Well, what if we move this point in? And let's say, instead of going between these 2 points, let's find the slope between this point, the closer one here. So now look at something like this. What will the slope between these, what will the secant slope be between these 2 points? Well, what's f of 1? 2. What's f of 0? It'd be 3, right? F of 0, 1, 2, 3 is right there as the y-coordinate. Over 1 minus 0. So it's negative 1 over 1, so negative 1 is our slope. Which secant slope looks like a better or closer, kind of like value to our actual tangent slope here? The slope of 0 or the slope of negative 1? Which one looks better? Negative 1, right? It's like much closer, right? There, the dotted line is negative 1. The solid line there is our kind of estimate for the tangent slope. Okay. Well, let's move this point all the way in then to this point right here. So let's move this point all the way in. So again, we were started here. We moved it in closer. Now we're going to move it in all the way. What's f of 1 minus f of 1 going to be? 0. Because again, 2 minus 2, right? So 2 minus 2 will give us 0 overall. What's 1 minus 1? 0. And what is this? Indeterminate form. Okay. Our slope formula fails us here. Right? Our slope formula fails us when we're trying to find the slope at a single point, because you have to use the same point twice. So that's it, right? Just give up. Yup. Give up for about 2 more weeks, Mr. Wade. Just about 2 more weeks. We'll be good. No! Flip the paper over. Okay. So let's reset up our scenario here. We had c plus h. We go out that h distance there. This has coordinates c plus h, comma, f of c plus h. This has coordinates c, comma, f of c. And then this has coordinates f of c plus h. Okay. So we saw earlier that, and just in that last example, if we bring this point in closer and closer, right, the secant slope between these 2 points, as we bring this point in closer and closer and closer to the actual point we're interested in here, we can get a better and better and better approximation of our tangent slope. Right? As we bring this point in, the secant slope will more and more closely resemble that tangent slope. Okay? Well, mathematically here, if we want to bring this point in, what should we do with h? Make it smaller. Okay? In fact, we want h to get closer and closer to what number? 0. What do we use in mathematics to approach something? A limit. So we'll do the limit as h approaches 0 of this secant slope. What was the secant slope? It was that right there, the f of c plus h minus f of c all over h. So f of c plus h minus f of c all over h. And oh my gosh, it's what we did for the warm-up. Okay.
Wow.
So while h will not equal 0, remember, if h is equal to 0, we're talking about the same point. We'll end up with 0 over 0 indeterminate form. We can instead approach 0, bring it in as close as we want it to be, and then that will allow us to come up with the tangent slope there by just approaching 0 there. Okay, so in summary here, as h approaches 0, the point c plus h comma f of c plus h gets closer to c f of c. As a result, the slope of the secant line gets closer and closer to the slope of the tangent line. Okay. So that's our final result there. Okay. So that allows us to find the tangent slope, right? But then, of course, given that point, right? So again, this being our point, where we're going to try and really find the tangent slope there, that also is a point, so we can find the actual equation of the tangent line if we wanted to. So if our function f is defined on an open interval containing c, okay, and if the limit exists, then the line that passes through the point cf of c with slope m is the tangent line to the graph of f at the point cf of c. Okay, slope m, that is the tangent line with slope m. Okay, so like this is the m that we're finding right there, the slope of the tangent line. Okay, the slope of the tangent line to the graph of f at this point, okay, is also called the slope of the graph of f at x equals c. Okay, so we could also say the slope of the graph at c is found by this. This is the slope of the tangent line at c, the tangent line to the graph, but it's also the slope of the graph at c. Another way you could call this, or the, well, in algebra 2, right, when you found the slope between 2 points on a curve, what was that called? What kind of rate of change? Average rate of change. In this case, since we're finding it at a single point, it's not an average over an interval here, it's at a single instant. This is the instantaneous rate of change. Okay, of f at c. So now we have the capability to find the rate of change of something at an instant. So for example, if you were given a function that described the position of a car at a certain time t, you could find the velocity of that car at any instant using calculus, at any instant of time, okay, using calculus, and very simple calculus too. Likewise, if you're given the velocity function for a car at any given time, again, using the derivative, you could find the acceleration, which is the rate of change of the velocity, right? You could find the acceleration of a car at any instant of time, given the function. Okay, pretty powerful stuff. So let's put this into practice, though. We're not going to worry too much about the applications in that sense just yet, but I do want to look at, just put this in practice here now that we talked about it. So, as an example here, I'll try and put it, here we are. Okay, so, let's say, for example, that we want to find the slope of the graph of f of x equal to 3x minus 1 at the point 2, 5. of the graph of f of x equal to 3x minus 1 at the point 2, 5. Now, we already know the answer to this. What's the answer? 3. Why? Because it's a linear function, right? It's in slope-intercept form. We know the slope of the curve. It's a line. Slope of a line is constant of the whole line, so the slope is 3. Okay. If we wanted to use calculus to do this, though, okay, and find the slope of the line using calculus, we're going to use that limit as h approaches 0 of f of c plus h minus f of c all over h. Okay. In this case, what is our c value? Remember, what was c in our earlier example here? C is right here. What is that? An x coordinate for that point at which we want to find the slope, right? We want to find the slope at this point, so the x coordinate was c. So in this specific case, in this specific example, c is what? 2. It's the x coordinate of the point of tangency there, so 2. So we'll plug 2 in. So there's our setup. All right, let's go ahead and plug this in. So f of 2 plus h, I'm going to plug 2 plus h in for x there. So it'll be 3 parentheses 2 plus h minus 1. And then minus f of 2. Well, what's f of 2, though? What's f evaluated at 2? 5, right? You can either use the point right there or literally just plug 2 in here. 2 times 3 is 6, minus 1 is 5. So I'll just do minus 5 all over h. So again, this became this. Okay, right? See, f of 2 plus h. 3 times 2 plus h minus 1. And then minus 5 of that. Okay. How can we simplify from here? What can we do? How should we proceed here? Yeah, distribute the 3. So 6 plus 3h. Minus 1 minus 5 becomes minus 6. What cancels? Well, the 6's will cancel. And what else will cancel now? What's 3h divided by h? 3. What is the limit as h approaches 0 of 3? There's no place to plug the 0 in for h, right? There's no h whose limit we're trying to find here. So it's just going to equal 3. Okay. Which is, again, no surprise. We already knew the answer to this, right? If you remember your Algebra 1, you knew the answer was going to be 3 anyway. But now we can show with calculus that it was also so. Okay. Questions on any of that? Let's try something more interesting, because that was like we already knew the answer ahead of time. Let's try something whose answer we don't know ahead of time. If f of x is equal to x squared plus 1, find the slope of the tangent line to f of x at the point 0, 1. Oops, I'm off the screen. There we go. Okay. So again, slope of a tangent line. So we're going to use the formula limit as h approaches 0 of f of c plus h minus f of c all over h. Okay. What is our c this time? What's our x value? 0, right? That's our point of tangency is 0. So we f of 0 plus h minus f of 0 all over h. What's 0 plus h? What's that going to be? Just h, right? So this is literally just f of h. Well, if f of x is x squared plus 1, f of h is going to be h squared plus 1, right? So this one's pretty nice because we had that x value of 0. Or c value of 0, I should say. So we get h squared plus 1 there, minus, what's f of 0? 1, right? So minus 1 all over h. What cancels or simplifies here? 1's cancel. And what about h squared divided by h? What does that leave us with? The limit as h approaches 0 of h. So that equals what? 0. The slope of the tangent line is 0. What kind of line has a slope of 0? A horizontal line. Now, let's take a look at what's going on here. I'll look at the graph. So let's look at x squared plus 1, specifically at the point 0, 1. There is x squared plus 1. Okay. This point 0, 1 is right there, right? Does it look like you have? Does it look like our tangent line? Does it look like we have a slope of 0 here? What do you say? Does it make sense? Yeah, I think so, right? If I graph, you can see right there it is. Okay, that's what that tangent line would look like. The slope there would be a slope of 0. Okay, specifically it goes through the point 1 though, but yeah, slope of 0. Okay? All right, I'm going to have you guys try one, and then we'll get you guys started on the assignment here. So you guys try, same scenario, find the slope of f at point -1, 2. So you guys go ahead and try that one. Same function. Find the slope of f at -1, 2. Give this one a try. See if you can get it set up here. See you, Nick. Homework's on Google Classroom, Nick. So you brought this H in, remember the H, sorry, you brought this X in from someplace, but it's, yeah, no X, so get rid of the X and you're right, okay, and then you're good. So yes. Right, so since you can't simplify this anymore, you have to do f of -1 plus h. So that's going to get plugged into the function right there, the x is still that same function. Now, f of -1 is 2, so you can replace that with 2. So, now I see. You're close here, but so f of -1 plus h. This is -1 plus h squared, but then don't forget there's also a plus 1 to the very end. Plus 1 to the very end. If you want, yes. Yes. Well, hang on a second. Yeah. Control C minus -1 minus 2. So it should be then, yeah. So it's 1, so 1 and then another plus 1 and then minus 2, so it should cancel out, which is 0. So now you can factor h out. I factor h out, cancel h. So say again. Yes, remember though, its limit is h equals to 0, so you're going to plug 0 in for h. Okay. Question? Yes.
I don't know what I did wrong.
You don't know what you did?
I did.
Okay. So, it should be C plus H, which would be negative. I see. Just use it.
Yeah,
That's fine. Okay. So then this is fine, but don't forget f is x squared plus 1. So you have another plus 1 in there. Right? That's x squared. Right? That's h minus 1 squared, but then there should be a plus 1 outside, and then minus 2. So it'll be 2 minus 2, they'll cancel out. Like it should be.
I know, I get what you're saying, but then wouldn't that's oh, because then okay, that makes sense.
Okay, so now it's gone, and don't forget to keep writing your limits here. Back on the H. A lot of work. I know, life is hard, but you can do it. Grace, do you have a question, or you just you got it?
Same thing.
Do the same thing.
We were working together.
Oh, I see.
Yeah.
You're using his paper.
Yeah.
I see. Mind meld. Gotcha. Okay. All right. -2 is your answer. -2 is your answer. All right. So, questions on that? Okay. The majority, so you will not be doing this for all of calculus, right? Okay. You're going to learn shortcuts. You're going to learn, different strategies and stuff like that, because this is just a lot, right? But for right now and for a portion of calculus, you will be doing it this way. Okay. So you keep that in mind. All right. Your assignment is posted to Google Classroom. So it's out of the book. but I even took a picture of that section from the book so you can just really just use your phone or your Chromebook, whatever you need to do the questions, okay? It's 9 to 15, the odds, so that's 4 problems.
Just one
Okay.
problem.
So, yeah, just 4 problems, that's it. Neat. Neat indeed.
I kind of know what it is, though.
Yes.